Welcome to the first lesson of Year 2 of A-Level Computer Science. In the first few weeks of this year, we'll be looking at binary maths. So we're going to begin by looking at how binary maths is related to how the computer stores data. In this lesson, we'll look at bits and bytes. We'll see how different data types are represented inside the computer. We'll look at the coding system used to represent text characters, and we'll look at how multimedia data are stored by the computer. The electronic memory of the computer is also called RAM, or random access memory. It consists of millions or even billions of microscopic circuits. These circuits can be either on or off. That is, they can be carrying a charge or not. All data is stored using these circuits. The circuits are organized into data locations. Each data location has a hardwired address. That is, the address is a number, but it will not change. It also has 8 of these on-off circuits, and they can change. As they change, that is what makes the data inside the computer. We represent the on and off circuits using the numbers 1 and 0. Obviously, there aren't actually ones and zeros inside the computer, just circuits that are either carrying electricity or not. Each one of these ones or noughts is called a binary digit, which we abbreviate to bit. So as I've said, the bits are arranged in groups of 8. A group of 8 bits is called a byte, and all the data in the computer is stored using bytes. On this course, we're only really going to look at binary numbers up to 1 byte long, but obviously in real life, the computer will typically join many bytes together. Most files and the computer's memory itself are composed of millions or billions of bytes. We use binary units to express file size, and here are the main binary units: kilobyte, megabyte, gigabyte, terabyte, and petabyte. Each one is 1,000 times bigger than the other. In the past, variations on these units were used that were 1,024 times bigger, but we don't use those anymore. This is the standard. This is the universal. This is the current universal standard. So let's imagine a set of 8 circuits. 3 of them are on and 5 of them are off, arranged in the pattern that I've shown here. This pattern of on-off circuits could be used to store the binary integer 67. Or it could be used as part of a floating point number. That requires 2 bytes, but if we're using default values, it would represent the value 0.53375. Don't worry, we'll learn much more about that later. Or it could just represent the letter C. So how does the computer know what this pattern of bits represents? The answer is that some other information that we have provided will tell the computer how to interpret the bits. For example, if we're writing a Python program, the data types of a variable represent the different ways of interpreting the bits. Sometimes an entire file will be composed of data of a particular type, and so as the computer reads that file, it will interpret the bytes in a particular way. And sometimes when a computer is only really used for one purpose, the hardware itself will have an inbuilt data type. One of the data types that we use is string data, and string data is composed of text characters. Text data is stored using a number coding system. Each character is represented by a different number. The coding system that we use throughout the world is called ASCII. That's been in use for many decades, and it's just become the common universal standard so that different computers can talk to each other. But that has now been extended to a system called Unicode. ASCII codes are sequential, so if you know the code for a capital A, you can work out the codes for all the other letters of the alphabet. Lowercase letters have a different series of codes. ASCII has 128 codes altogether, so that's all the letters of the alphabet, and most of the other keys that you can type on your keyboard have got their own ASCII code. Digits have their own ASCII code. The ASCII code isn't the numerical value of the digit. Instead, it's just an arbitrary code number that tells the computer you've typed that digit. To show that we're not talking about the number values, but we're talking about the symbols, they're shown in quote marks. This will look a bit familiar to you because you can have strings in Python. Inputs are all strings and you have to convert them into integers, change the data type before you can use them in calculations. Unicode extends ASCII to include thousands and thousands of other codes. However, the first 128 codes of Unicode are the same as old ASCII. That means old files from decades ago can still be read by modern computers, so that was a really good decision. But Unicode is better than ASCII because it includes a much wider range of characters. Well, there are a few different versions of Unicode, but the most common one is called UTF-8, and that's used by over 90% of websites. And this uses a variable number of bytes. So if it's using the old ASCII code, it just uses 1 byte, but it can extend up to 4 bytes long, which gives us more than 4 billion different codes. And by no means are all these in use at the moment. But all the different things that we can represent are included in Unicode. For example, all global alphabets, including Braille, lots of different symbols, and all the emojis that we're familiar with. Who decides what symbols have got what code? Well, it's an organisation called the Unicode Consortium. They don't have any legislative power. They can't force us to use particular codes. But the whole point of Unicode is so that computers can talk to each other. So if I want a new alphabet or a new emoji to have its own code, I need to get in touch with the Unicode Consortium and try to persuade them to include my language or my symbols in their coding system. If they agree, they will allocate some codes to my symbols, and then they will send an update to all the computers in the world, and they'll be able to read my symbols. The set of all the symbols that have got a Unicode is called the Universal Character Set. I've included a couple of URLs there so that you can have a look at all the different charts and tables of Unicode values. Here's one very small example. It's part of the emoji table and it's various different cat faces. The number at the front isn't the Unicode value, it's just the number of these emojis in the table of emojis. The second column shows the codes and they're given in hexadecimal. We'll learn about hexadecimal next week. You may know it already. And the final column shows the symbol that will appear in your browser if your computer receives that Unicode value. In fact, different processors and operating systems interpret Unicode numbers slightly differently. So here are 4 of those cat faces, and you'll see that an Apple phone or Twitter, Facebook will interpret and display those emojis in a slightly different way. You can use Unicode in Python if you like. There's 2 Python functions, ORD and CHR, and ORD will turn any character into a Unicode symbol, and CHR will turn any number into the appropriate Unicode character. However, idle, the URL that the IDE that we use can't display all the Unicode characters. It can do quite a lot of them though, so it is quite interesting to explore. You could, for instance, generate large random numbers and see what they look like in Unicode. I'm just coming to the end now, but as well as character files, you can also have other kinds of multimedia files, and they are all stored using binary integers. Images are stored using a color code, so each pixel in the image, each dot in the image is stored as a number which represents the color of that dot. Sounds are stored, we will do more about this in a later lesson, but sounds are stored as numbers which represent the amplitude and frequency of the sound, amplitude and pitch of the sound, and videos are stored by recording thousands of images plus a soundtrack and combining that to make a video. A big issue with multimedia files is that high quality files take up more space, and if we want our files to be very compact and small, they often lose image quality or sound quality. Again, we'll come back to this another time. So to recap, in this lesson we've looked at what bits and bytes are and the different units that are used to represent groups of bytes. We've looked at how a single byte can be interpreted in different ways according to its data type, and how ASCII and then Unicode are used to represent text data. Finally, we had a very brief look at how multimedia data can be stored in binary form. So here are some activities for you to try in this first week. If we get a chance in class, I'd like us to just do this on paper, send and receive messages using ASCII codes and read each other's messages, and write Python programs which will read and write ASCII code sequences. If you've got time, use a random number program to explore some of the different Unicode values that you might not know about, and write a program that will convert any character into ASCII code and then represent it as a binary integer. So I've included quite a bit of programming activity in there because I want us to keep our programming skills sharp as we go through the second year. Okay, so one more lesson this week. Look out for it on YouTube. Bye for now.